In this video we will see how to sketch the surface z equals x squared plus y squared. We see that z is a function of two variables x and y. The independent variables are x and y. What we do is we fix both independent variables at a certain value. We will start by fixing x. We will fix x at the value x0, and then we consider what we get. So here we just have a function of one variable. Z is a function of y only. Now if x is fixed, then we need to consider all points on this plane. So we saw in the last video that when x is a constant, then we have a plane that's parallel to the yz plane and cutting through the x-axis at x0. So all points on this plane have the property that their x value is a constant, and that constant is given by x0. So we want points on the surface whose x value is x0. Those points on the surface will be the intersection of the surface with this plane. So we will get some type of curve. We actually get a parabola, because this is the equation of a parabola. So to write things in a more standard form that we're used to, z is our dependent variable, vertical axis. Y is the independent variable here, horizontal axis. And we have a constant c, which we know is x0 squared. So we are used to seeing graphs like this, except we see them given as y equals x squared plus a constant, but it's just a change of letter here. We know that they have this shape. When c is 0, we just have the graph of z equals y squared, and that's a parabola that cuts through the origin. If c is 1, we have a similar shaped parabola but cutting through z equals 1. Basically we just raise this one up by 1 unit. So in general then, with c equal to x0 squared, we have a parabola that cuts through the z-axis at x0 squared. So this is what we get. Well, of course, except that we are not cutting through the z-axis now, but through a plane as parallel to the yz axis. So the minimum value of the curve will be x0 squared. That's when y is 0. So this curve is a parabola. It's meant to be this one here. Has the shape, same shape as this one. It's just displaced away from the yz axis. So here's a cross section of the paraboloid at x equals x0. But of course we can vary the value of x0 and consider many other cross sections. If x0 is 0, for example, the cross section will be a parabola going through the origin. It's actually this one here. If x0 is negative, we will have parabolas that are behind the yz plane. You can see that as x0 increases in magnitude, the parabolas get higher and higher above the xy plane. So for large positive x0, we might have a parabola like this one here. For large negative x0, we have this one here, which is behind the yz plane. But you can see that x0 squared is going to be the same whether it's positive or negative, so we will see a symmetry in the distribution of these parabolas. The distribution of these parabolas is actually symmetrical about the yz plane. Next we consider fixing the other independent variable. We fix y and we call its fixed value y0. So we get z equals x squared plus y0 squared. So these are also parabolas. They have exactly the same shape as before. But now we are considering the planes y equals y0. So for these parabolas, the y values are a constant, and points that have a constant y value lie on planes that are parallel to the xz axes. So this plane here cuts the y-axis at y0. So the equation of this parabola here is z equals x squared plus y0 squared. The y value of the points on the cross section is the same. When x is naught, the lowest point on the curve is given by z equals y naught squared. So this distance here is y naught squared. So if y naught is equal to 0, for example, we will have a parabola that's going through the origin, 0, 0, 0. So we will see a symmetry again as before, because y naught squared doesn't depend on the sign of the y value. So for large positive y values, y naught squared is going to be big. For large negative y naught values, y naught squared is also going to be big, and it will have the same value. So we'll see a symmetry in the distribution of these parabolas about the xz plane. So now we can put both sets of parabolas together. The parabolas that are parallel to the zy plane and the parabolas that are parallel to the xz plane. In this picture, the dotted parabolas are the ones that are parallel to the xz plane. To get a better idea of the shape of the surface, we can also consider fixing the dependent variable z. So let's fix z at the value z0. Z equals z0 is a plane that is parallel to the xy plane and cuts the z-axis at z0. So all points on this plane have the property that their z value is the same. It's a constant. It's equal to z0 in this case. So we are interested in points on the paraboloid that have the property that their z values are constant, z0. Those points on the paraboloid will be the intersection of this plane with the paraboloid. So we will get equations of this form here. The x and y values of those points on the paraboloid must satisfy this equation, but this is nothing other than the equation of a circle. The equation of a circle centered at the origin of the xy plane and with a radius of r is given by x squared plus y squared equals r squared. This just comes from Pythagoras' theorem. So if r is equal to z0, it means that we are dealing with circles, actually circles of radius the square root of z0. So this number is the square of the radius. So the planes that are parallel to the xy plane will intersect the paraboloid at circles, and the radius of those circles depend on z0. So z0 is the intersection of the plane with the paraboloid. So the bigger the value of z0 is, the bigger the radius. The radius is the square root of z0. So the smallest value for the radius is 0. That's when the plane is just the xy plane. So z0 is 0. So the radius is going to be 0. So the radii of these circles does not increase linearly with z0, with the z coordinate, but as the square root of the z coordinate.